Okay, in this problem, what we're going to do is try to combine something from section 12.1 and 12.2 using the kinds of things in two variables we saw and the kinds of graphing that we're actually doing right now. Here's the problem. It says describe algebraically and geometrically the set of points whose distance to the point 0, 0, 1 is equal to the distance between that point and the xy plane. All right, I'm going to draw a picture, just enough of a picture to be able to do it, and we'll see what happens. So here's what they want, right? I'm going to add some axes, and then I'll have to take them back. The point 0, 0, 1 is right there. And what they want to do is look at every point whose distance to this point is the same as the distance down to the xy plane. So let me draw one where I think it kind of looks reasonable, where this distance is equal to this distance. Now we're looking for points x, y, z. And we're going to have to do two different kind of distance formula, right? The distance between the point x, y, z and the plane is actually absolute value z. Because if the point was way down here, it would actually be negative z. The distance between the point x, y, z and the point 0, 0, 1, let's see, that distance is going to be what? It's going to be the square root of x minus 0 squared plus y minus 0 squared plus z minus 1 squared. Like that. And so what they're asking for is the set of points where this distance is equal to this distance. Now what I'm going to do is just write that all at the top. Yeah, I'll erase first. And see what if we can't figure out what we're looking at. I want that the square root of x squared plus y squared plus z squared equals the absolute value of z. Now, I'm going to say I'm uncomfortable with this for two reasons. I don't like the absolute value and I don't like the square root. So I'm going to square both sides. When I square the left-hand side, I just get x squared plus y squared plus z minus 1 quantity squared. When I square the right-hand side, I get the absolute value of z squared. But if z is negative I squared, I get z squared. If z is positive I squared, I get z squared. So this is just z squared, and that got very comfortable very quickly. Now, that certainly is algebraically, but I don't recognize it yet. I can expand that middle thing there. So I'm going to try that. This is exactly actually what you did when you did conic sections back in algebra. This is going to be z squared minus 2z plus 1 equals z squared. The z squareds cancel. I'm going to throw the z over. And so what I'm going to get is 1/2 x squared plus y squared plus 1/2 equals z. So algebraically, I think that's as simple as I can actually make it. Geometrically, what is this? Well, we know what z equals x squared plus y squared is. That's a bowl. Yes. Taking half of that just makes it still a bowl. It just goes up half as fast. Adding 1/2 to it just lifts the whole bowl up 1/2. So what I'm getting is a bowl that goes up slower than a normal bowl, but whose bottom is at 1/2. Now, if we're going to draw the picture here, it just looks like this, right? Remembering that the point 1, 0 is right here, and the axes, this one runs right through like this, and goes down like this, and goes down like this. And so geometrically, it's just a bowl. And by the way, this is very, very similar to the definition of a parabola that comes from the Greeks. So there it is, algebraically and geometrically, a surface that's defined using distances.